Hello, everybody, and welcome back. So we need to talk about the reagents that are necessary for the camphor production in this laboratory. And on the screen, you see a couple of structures to the right-hand side. And we need to talk about the first one up at the top. Now, this structure is isoborneol, I-S-O-B-O-R-N-E-O-L, isoborneol. The molecule smells like dirt. Okay, if you don't believe me, when you get the isoborneol in the laboratory, I want you to take a big old whiff of the jar because you're going to quickly find out, yeah, it smells kind of dirty. All right, so if you take a look at that structure is very similar to camphor, right? If you go back and take a look at the structure for camphor and you compare it to the isoborneol molecule, what you're going to realize is that there's one area of the molecule that's different. Right? We still have this six-membered ring structure, and you're going to see that here on the screen. Again, we're looking at it on the side. So 1, 2, 3, 4, 5, 6. It's bent over like a sheet of paper, right? And then one carbon is connected to the other carbon across the way in form of a bridge. And we saw the same thing happen with camphor as well. And that connector carbon up here at the very top has two little antennae that stick out, right? So the antenna are basically other carbons. And we saw that camphor had that similar structure as well, right? So if I go back and take a look at the structure for camphor, basically it's the exact same thing. Here's a ring, there's a bridge, there's a carbon up here that attaches those two things, and there's CH3 groups, which we called methyl groups, that hang off of that in addition, right? Okay, so if I take a look, here this front carbon toward me has a methyl group that's pointed out, a CH3 group, and in camphor, that was the same thing, but the area that's different is here to the right. This isoborneol, again, OL. OL means alcohol, for the most part. And that alcohol group is an OH group. And if you take a look at the structure, that's why you see the OH group that's there. So you see the same functional group happening over and over and over and over and over. It gets quite boring after some time, right? So that's the isoborneol group, and that's what we're going to start with. And we're going to have to get rid of the OH group, and we're going to have to replace it with a double bond O. We said that was a carbonyl, and in campphor's particular case, this carbonyl is a ketone group because that carbon has a neighboring carbon to the left and a neighboring carbon to the right. And that's what makes it a ketone. And that's what we talked about in the previous video. So we need to take this alcohol and we need to convert it to a ketone. And in order to do that, there's a number of different ways. One of the probably most common way that they will tell you in a textbook is to take chromium acid or chromic acid. Now the problem is that chromium is a environmental hazard. We never really want to dump chromium down the drain. Just ask Erin Brockovich and she'll tell you all about it, right? So chromium, well, if we can substitute that with something else that does the job like chromium would, then all of a sudden we could have some products that we could dump down the drain. And that's what this lab is all about. It's taking something like chromic acid, getting rid of it, and showing you that there's other better ways to produce the same type of molecule. And in this case, we're using hypochlorite. So hypochlorite is shown below. That's sodium hypochlorite that you're seeing there. And that sodium hypochlorite, the hypochlorite part, is the OCl. It's a very common cleaning agent. You're going to see it in a lot of toilet bowl cleaners. You're going to see it in pool water cleaners. And you're also going to see it in your laundry detergent cleaners known as bleach. So it's a common disinfectant. It's a common cleaner. It's a common bright whitener. You name it. This is a common molecule. And we know good and well we can put hypochlorite down the sink, right? If we put it in our washer, and that washer machine basically empties into the drain, then we know that this is not going to be an environmental hazard like chromium would be if we use the previous mechanism or synthesis route. Okay, so let's talk about the mechanism and the reaction and how this goes forward. So isoborneol is up here at the top. There's your OH group. And hypochlorite is going to be added in with a little bit of other stuff. And all of a sudden, this is going to convert over to a double bond O, not an OH. So the way I want you to think about this, even though it's not really true, is you're just removing the hydrogen here, right? If this hydrogen can be removed, and a double bond forms between the O and the carbon that it's already attached to, then all of a sudden we get camphor, and that's really all that we need. But the mechanism is actually more complicated than that. It's not just removing of the hydrogen. There's a lot more steps that go on in this mechanism, and we're not really going to talk about the curvy arrow for that. Okay, so isoborneol and hypochlorite, you need to control the temperature, never above 50 degrees. So this is very important. If you're in the laboratory and you're doing the synthesis, you're going to get to a part in the procedure where it says monitor the temperature at 50 degrees. You never want it to go above that temperature because side products can happen. And if side products happen, then your purity plummets and you want a very pure compound with this. So you have to be very temperature sensitive. Again, it's kind of like baking a cake. If the cake says put it in the oven at 350, and you turn the cake oven on at 400, well, the cake's going to bake, but it's not going to bake the right way, right? The same thing is happening here with these molecules. So that hypochlorite addition is going to begin to convert that OH to a ketone, or in particular, a carbonyl, which will form the ketone at the end. So you want to make sure that you add enough hypochlorite. And there's going to be a part of the procedure that will say you're going to start off with bleach, you add some bleach, and then later on throughout the experiment, you're going to test the solution with potassium iodide paper. And that paper will turn blue-black if bleach is still present. All right? So let me kind of draw that out for you so you know what we're kind of talking about here. Maybe I can explain it better with a picture. So let's say that you have a flask, and this flask is going to have your isoborneol in it, and you're going to start off with some bleach, and it's going to tell you how much. And you're going to let this stuff stir, and basically react together, right? And you want to put a thermometer in it, and you want to make sure that it doesn't ever go over 50 degrees. You want it to stay under that, so that way this product will form the proper way. So the problem here is that depending on how much isoborneol that you start with, and depending on the reaction conditions, this reaction could go a little bit faster. It could produce a little bit more product than what you expected. So because of that, we have something called potassium iodide paper. And this is very similar, Ki paper. It's very similar to pH, but it's not really working off of a pH unit like pH paper would, right? Its whole purpose is to determine the hydrogen content. Well, that's not what we want here. We want to determine the bleach content. Is bleach still there? Yes or no? So the potassium iodide paper, what would happen is that I would take a drop of this solution at any point in time, and I'm going to put that drop on the sheet of paper, just like I do with a pH strip. And if this spot turns blue, dark blue, or maybe even black looking, then this means, yes, bleach is still there. So as long as bleach is still there, then this reaction goes forward. And that's good news, right? At the point where I lose bleach, the reaction stops. Now, the problem is that maybe all of my isoborneol has not converted over to camphor. So at any point in time, if I put a spot on the paper and this spot does not turn blue-black, then that means there is no bleach left over for the reaction. And if no bleach is there, then that halts the production of the camphor. No more camphor is going to be made. So it's very important that you take care in monitoring the reagents in this reaction. They're very particular. They're very picky, right? Temperamental. You want to make sure that you have enough, and in order to do that, You use potassium iodide paper every single time. And the lab's going to tell you, every so many number of minutes, check it with the potassium iodide paper. And if it turns blue-black, keep on going with it. Not a problem at all. If it doesn't turn blue-black, you add more bleach. And when you add more bleach, the reaction will start again, and it will start converting some of that extra isoborneol over to camphor, which is what you want. Again, you want a very pure product here if you can help it. Okay, so that's the story with the potassium iodide paper. You've never used it before, probably up to this point, and this is a new technique for you. And the purpose of this is to kind of help you realize there's other indicator paper out there besides just pH paper. There's tons of different options. All right, so that's going to make sure that we have enough for this reaction to go to completion. So neutralization. After the reaction time, okay, when you know good and well that there's no more isoborneol left in the flask because you've let it stir as long as the lab has told you to do it, you're going to check the pH or the Ki paper one more time. And you'll put another drop on it. And if it goes blue-black, that means you have extra bleach, right? All of your isoborneol has converted to camphor. But that last test, if it's blue-black, means that there's extra bleach that's lingering around, and we need to get rid of it. We don't want that extra bleach involved in the process after this point. So what we do is that we neutralize it. We kick it out. We make it react and we make it break down so that way we can take this sample, this container, and then go to the next step of the process. But you've got to neutralize the extra bleach first. So all up to this point, you're testing. If you don't have enough bleach, you add more. If you don't have enough bleach after the second time, you add more. Maybe you test it a third time. If there's not enough, you add more. And then at the very end, if you still have bleach left over, you need to get rid of it. You need to neutralize it. And you do that by using sodium bisulfite. So the lab is going to tell you what concentration of sodium bisulfite that you need. Have it on hand. That way, if it is extra bleach in the very end, and very often there is, you can just add a few drops of sodium bisulfite to it. That will take care of it. It breaks down the bleach, and you don't have to worry about it anymore. Okay? So that forms these byproducts that will then get cleaned out and washed out and rinsed out of our camphor. All right. So after that process, we now need to get our crystals and we need to clean them. So isoborneol has started off with a solid. You've added some bleach and liquid to it. It probably dissolved up a little bit. And then over the course of time, as the reaction proceeded, you probably have seen a solid form yet again in your container. This new solid is the camphor product. And the decomposition of the bleach also has some byproducts that's in the liquid solution. So we need to separate the camphor solid from the rest of the liquid. So we're going to pour it through a Buckner funnel. This you probably have used already. And the directions are going to say cool the product in an ice bath and then take it through a filtration system. So make sure that you record the temperatures, make sure that you record the time that it stayed in the ice bath, make sure that all of that is logged into your lab notebook. You don't want to lose any points out of it, and wash it with very cold water multiple times. So this means that camphor is not water soluble. That also means that camphor is probably not polar. And if you take a look at the structure, it isn't. It's mainly organic with one little double bond O that's present. And all of the non-organic parts outweigh that one little oxygen that's hanging out there, right? So after you rinse it really, really well, you're then going to dry it overnight. Do not put it in the oven. This stuff has a very low melting point. And if you put it in the oven, all your stuff is going to evaporate away and you'll never see it again. And it's going to cause a problem with the lab and our oven because now you've just put camphor crystals everywhere in the oven on all parts of the glassware that's on the inside of it. So after that, you're going to weigh it and then you're going to do a melting point of it. Now that's the crude product, right? You've not done anything to clean this product up at all. This is just your raw crystal that you've gotten from the reaction. So you're going to weigh it and then you'll do a melting point and you'll record those values down so that way you can report a yield and that way you can report a melting point of the crude. Now, the last part of the lab is going to be purification. The purification part basically wants you to do an advanced lab method. And that advanced lab method for us is sublimation. All right, so what does that mean? What does sublimation mean if you've never heard of it before? All right, so let me clear off the screen. So in general chemistry, you have taken a solid and you've learned that solids can change over to liquids, and this is a melting point, right? So my solid will melt into a liquid, and then the liquid can change to a gas, and that's through the process of boiling. So it would have a boiling point in order to get there. However, some chemicals in a laboratory do not show the middle step, meaning that you can take a solid like solid camphor and you can heat it up. And when you heat it up, you bypass the liquid stage. No more liquid stages there. It goes straight to a gas. That's kind of weird when you think about it, right? We're so used to seeing a solid melting to a liquid and then going to a gas. But in Camphor's case, as well as a handful of others, when you heat the solid up, you'll never see a liquid. The boiling points and melting points are too close together for you to distinguish them apart. So it automatically goes to a liquid and then to a gas all at one time. All right? And you just see it turn to a gas. What we call that is sublimation. So sublimation is the process that camphor will undergo, and you will be doing a sublimation step in this laboratory to purify. So many times recrystallization is necessary. You've already seen this, right? You've generated some product, you've recrystallized the products, you've gotten better numbers because of it. That's what we're after. There's no recrystallization here, though, because this stuff will not recrystallize in a way, right? We're not going to dissolve it and then bring it out of solution. Well, what we can do, though, is sublime it. So we're going to heat this stuff up. And as we heat it up, it will go directly to a gas. And it leaves behind all the crud. And if there's a way that we can make that gas condense onto a different piece of glassware, then we've separated the pure camphor from all of the crud and contamination that might be present. So if you go to the back of your lab manual in Operation 29, it's going to give you some pictures of the sublimation process. And this is kind of what a real sublimation piece of glassware will look like. We're going to do it a little different in the lab, though, and we will walk you through that when you get to that point. But what you're seeing here is that you would put crystals like camphor down here in the bottom of the test tube. And then this test tube will be heated. That's why you're seeing that as a red area down here below. And that's what you're seeing here in the real life picture, right? Here you see some solid, and then down below you see a Bunsen burner head that you're heating up. So this solid is going to quickly convert over to a gas, and that gas will eventually creep up the glassware, and it will attach itself onto a very cold stem. There's another internal piece of glassware that's right here at the very top, and that constantly gets cold water. And that cold water makes that piece of glassware cold, of course, and that gas will condense onto that piece of glassware, and that will make my solid form again. So what I'm doing is that I'm subliming to make it pure. I'm heating it up, all the gas leaves, all the stuff that's not camphor stays behind, and it will probably turn colors. It will turn yellow. It will turn black. It will get thick and soupy. Maybe it will look a little burnt or charred, but that's the contamination that's in your sample, and we want to get rid of it. So heat it up. All the camphor will escape to a gas, and then it will condense back down onto this cold piece of glassware. Now, again, we will not use this type of setup in the laboratory. What we will have instead is a beaker, because you'll have so much product. And that beaker will be heated. And then on top of the beaker will be a very cold watch glass, probably with an ice cube on top of it. So your crystals will actually cling to that watch glass and hang out until you're ready to take the watch glass off and flip it over to scrape your pure camphor crystals off of it. So the key here is to slowly heat. right? You don't want to heat this stuff up too quick, because if you do, bad news for you, you're not going to get a good separation and you're not going to get a very pure product. Scrape it off, replace the watch glass if you have to, and then repeat the whole process over again, because there's a chance that your watch glass will run out of room and your crystals can't cling to it anymore. So when that begins to happen, you need a fresh watch glass that can put into its place, that can gather more crystals on top of that, so that way you can really increase your percent yield here. So you want to be careful when you scrape off the crystals. Every crystal that you lose, that's percent that you're losing as far as percent yield goes. So your technique is going to be very important here. Sublimation, here are some extra pieces of glassware or glassware setups that you might see in a lab. These might be a little bit more detailed, but they're all doing basically the same thing. You've got a container, it's a closed container, there's an internal piece of glassware that's staying cold, and then that piece of glassware is going to capture your crystals through the sublimation process. No matter if it's A, if it's in the middle for diagram B, or if it's at the end for diagram C. Right? Same stuff, just different ways of doing it. That's all that it is. It's basically, how much money do you want to spend on this glassware? That's what's going to determine it. Sublimation before and after. This is basically what you're going to see. So to the left, the crude product is going to be clumpy. It will be rocky. It will look like sugar in a way, but it will be kind of fluffy at the same time. But I want you to understand that isoborneol takes a similar type of look, right? So this is going to be isoborneol as well as camphor, as well as all the other byproducts that were generated in the reaction. So we need to clear that up. We need to clean it up. We need to pure it up. And we need sublimation to do that for us. So to the right-hand side, that is what the actual camphor should look like. They will be crystals. They will not be rocky. They will not be pebbled shape. They will almost be individual type of crystals. It will be a very fluffy powder that you will be scraping off of your watch glass. So the looks of the two things are different from before and after. And your melting points will also be different before and after. So your melting point for your recrystallized or your sublimed camphor will be much better. So the lab scenario, Northern Pines Chemical Company wants to test a new synthesis route. They want to eliminate the chromic acid and use a more green route, which includes bleach. So camphor that they currently make is 95% pure. So they're going to let you basically use bleach, and they're going to want to know, can you get 95% purity out of this using bleach as a reagent instead of chromic acid as a reagent? And if so, then bleach is going to be a very good substitute for the environment or the hazardous chromic acid that's used in the old process. So your job, make camphor from the oxidation of isoborneol and obtain a product that's 95% pure. The conformation of the product will be determined by melting point. So camphor should be melting at 179. The isoborneol should be melting at 212. So if your product is melting close to 179, then that means, hey, this is pure camphor, this is pretty good, but your melting point is really going to determine that case. So how do I calculate the purity? Well, the purity is going to be given into the lab background. You're going to see an equation, and it will say change of T is equal to Kf times M. Now, Kf and M represent something very special. The Kf is going to be the freezing point depression constant. So that number is 40. So a 40 will go in for Kf every single time that you use this equation for camphor. The melting point difference is going to be the change of T. All right? So let me kind of draw this out for a minute. Change of T equals K times M. So change of T is going to be the temperature difference. So let's say that your product should be melting at 179 because that's camphor's melting point, right? But let's say that when you do it, you actually got 171 instead. So you take the difference here, 179 minus 171, that's 8 degrees. and 8 will go in for change of T. The K will always be 40, and then the M is what you're solving for. So the M, if you take a look at the variable, represents mole of isoborneol per kilogram of camphor. Mole of isoborneol per kilogram of camphor. So I'm going to write this unit over to the side. Mole of isoborneol per kilogram of camphor. And we need to calculate purity. All right, so if I take these numbers the way that I have them here now, and I take 8 divided by 40, that's going to give me a 0.2 as an answer. So that means that there's 0.2 moles of isoborneol per kilogram of camphor. So how do I change that to percentage, right? We want 95% or better as far as purity goes. Well, the 0.2 mole of isoborneol, that has to be converted over to gram of isoborneol. And you know how to do this, hopefully, right? You've got mole, you need to get to gram, and you need the formula weight in order to do that. So once you get that number, that will go here. That will tell you how many grams of isoborneol there is in that sample that you melted. Then down below, this is kilogram of camphor, right? So if that's kilogram, then that is 1,000 grams of camphor. So to calculate percent purity, you take these two numbers and you divide them. Whatever number you get here, divide it by 1,000, and then multiply by a 100 because you're getting percentage here. And that is the number that we're looking for. It's got to be greater than 95. All right? So that's the calculation that you'll be doing in the lab. It's kind of different than all of the other lab experiments that we've done up to this point. So a couple of thresholds here that we want you to meet. Number one, we want your overall yield to be greater than 60%. So we're letting you slide by with less than 2/3 of the product. Okay? The purity, though, we want you to be greater than 95%. So you have to be taking extra care in subliming your product to make that pure camphor product. And your melting point error should be less than 3. So the purity and the melting point here kind of go hand in hand. Typically, if you pass one threshold, you pass the other. If you fail one threshold, you fail the other. But those are the 3 things that we're going to be looking for in the camphor lab. All right. So remember, camphor is typically cosmetic. Camphor can be typically the food industry as well if you're outside of the United States. And you're going to be making this product that you can then take. It will smell wonderful. You can bottle this stuff up. You can take it home if you want to, or dump it down the sink. We really don't care what you do with it. But that's the Camphor Lab in a nutshell. So if you've got questions with it, let us know. We will help and guide you through the sublimation process, especially since you've never done it before. And I think that you'll enjoy the lab at the same time. It's pretty easy, and it can take care of itself. The sublimation will require your attention a little bit, but everything leading up to that point will be perfectly okay. All right, so easy setup, easy lab, and as long as you get your purification step down pat, I think that one time through, this lab will be an A for you. So good luck.